everybody, and welcome to our Cloud Chamber Particle Detector Lab. It's kind of a virtual lab or a video lab, but that's how it goes right now. So I have a presentation for you about this detector, and then I'm going to mix in videos of me carrying out the lab from my kitchen, and you'll get at least an idea of what goes on. I'll have some links to resources for making your own cloud chamber if you're interested. So our objective for this lab was to build a cloud chamber to visualize, that's a typo, ionization trails of cosmic rays and naturally radioactive particles, and then to classify those particles based on their trails, their characteristic trails. So the background for this cloud chamber, the experimental detectors at the Large Hadron Collider, LHC, or the Deutsches Elektronik Synchrotron, DAISY, are immense, complicated, and expensive. But similar particle detectors, like the Continuously Sensitive Diffusion Cloud Chamber, that's the full name for this apparatus that we're making, can be made and operated in your own home or school when it's open. It was developed at UC Berkeley in 1938, and what happens inside is that evaporated alcohol is making a cloud, and passing charge, it's almost more like the evaporated alcohol makes a fog, and passing charged particles leave a visible trail, like a cloud trail as they go. So the alcohol, there's isopropyl or rubbing alcohol absorbed by felt at the top of the chamber, and it evaporates into the air inside. As the evaporated alcohol sinks towards the cold, dry ice layer at the bottom, it cools. As it sinks and cools, it wants to turn back into liquid, but it can't get out of its suspended state. The air and the alcohol vapor become supersaturated. So the atmospheric alcohol will now form cloud-like droplets on anything it can cling to. When a charged particle flies through the chamber, it bumps into an atmospheric molecule and knocks off some of the electrons. That air molecule then becomes a charged ion. The atmospheric alcohol is attracted to the ion and clings, forming tiny droplets. The resulting track of droplets is what we see. So you're seeing this cloud trail as the particle ionizes air molecules as it passes through them. So these are the types of tracks we expect to see. And obviously these are idealized cartoon drawings of the tracks. I am also attaching or including a link to a document that just has these cartoon drawings and descriptions for your reference, because you're going to be watching the videos and identifying particles by the tracks you see, or trying to anyway. So short and fat is one of the options. Atmospheric radon atoms spitting out, and what you're seeing is atmospheric radon atoms spitting out an alpha particle. So radon is a naturally occurring radioactive element, but it exists in such low concentrations in the air that it is less radioactive than peanut butter in total. There are certainly houses, and especially I guess in the Salt Lake Valley, that tend to have more radon than normal, and you can get a radon testing kit. When I lived in Sugar House, our house had extra radon coming in through the basement, right, coming in up through the ground. And then we had to do radon treatment, which meant we had to have a vent out of the basement. We had to have fresh air into the basement. So alpha particles spat out of radon atoms are bulky and low energy, so they leave short, fat tracks. And you're remembering that an alpha particle is actually 2 protons, 2 neutrons, aka helium. In comparison to other radiation, alpha particles are heavy because they're made from those 2 protons and 2 neutrons. And due to their size and low energy, they don't travel very far, and they produce short tracks, but they're very massive, so they ionize a lot. You might see a zigzag or a curlicue. That would be a track of an electron or positron. Electrons are also called beta particles. See the previous lecture on particle physics. Electrons and positrons are created when a cosmic ray crashes into atmospheric molecules. Electrons and positrons are light, and they bounce around when they hit air molecules, leaving zigzags and curlicues. So you're seeing the path of bouncing. The tracks are a lot longer than the alpha particle tracks because the electron or positron is much lighter compared with an alpha particle. You remember, hopefully, that an electron is something like 2,000 times lighter than a proton or neutron. And so 2,000 or 4,000 times, in any case, a lot lighter. So then an even longer straight track is evidence of a muon. And you remember that muons are electrically charged like electrons, but they're heavier, right? They're the second generation of leptons in that electron muon tau series. They're produced when cosmic rays bump into atmospheric molecules high up in the atmosphere. And because they're so massive, muons just mash their way through the air and leave a clean, straight track. So they don't bounce off of the atmospheric molecules the way electrons and positrons do. They're less deflected by collisions with air molecules. Finally, you might see forked tracks. I've made a bunch of example cloud chambers in my house, and I've only seen a really clear forked track once. These tracks are the signature left behind of a particle decay. And as we've learned, many particles are unstable and will decay into more stable particles. So when you see a forked track, you might be seeing a decay. So a particle starting as one thing, decaying into two others. Kind of especially magical. So that's the end of the PowerPoint of the lecture. You're going to watch my video version of this lab, and then you're going to watch some videos of professional cloud chambers under sort of ideal conditions. And throughout all of that, you're going to be trying to identify particle tracks. Hi, everybody. Welcome to my kitchen. We're going to do physics from my kitchen today instead of the lab I had planned for in class. We'll see how this goes, and maybe we'll do some regular kitchen physics. Today we're going to build a cloud chamber and look at particle tracks left behind as particles pass through and ionize some supersaturated alcohol vapor. So the way we're going to make this supersaturated alcohol vapor is to set up a big temperature difference. So we'll have a very cold bottom and a pretty warm top of this closed airtight tank. And then there'll be a pad saturated with rubbing alcohol at the top of the tank, which alcohol then evaporating into the air in the tank creates the conditions for the track formation. So much of what we're using today is pretty accessible, and you could definitely do this at home. I'll give you some links to information about where to get materials and how to put this together if you're interested in seeing it for yourself. It's really kind of magical to see these tracks. The only thing you're going to have a hard time right now getting is the isopropyl alcohol, the rubbing alcohol. I happened to have this bottle left over, and it's definitely a pre-COVID-19 situation to have that rubbing alcohol. But maybe you can find something on Amazon. So in any case, we're interested in safety. We're going to be working with the rubbing alcohol and dry ice. So I've got my safety glasses on that I managed to grab from the classroom before the building got shut down. And whenever I'm working with the dry ice, I'm going to use some mitts, some oven mitts. So the first thing is that we're going to make a bed of dry ice. And I usually prefer to have blocks of dry ice, slabs of dry ice. I have the dry ice, usually the slabs of dry ice are on top of some kind of insulating material. My packing peanuts are now kind of mixing with the dry ice chunks in a way that I'm not sure is going to be good, but I'm trying to create a layer of dry ice. And then on top of that dry ice, we're going to put a metal plate. So this is a piece of aluminum. It's probably 1/4 inch thick. It's been anodized on top. The important thing is that you have something that's heat conductive, and something that's relatively dark on top helps you see the particle tracks once you set it up. And it becomes loud. Smoke that out. That is very disturbing to my lab assistants. The guinea pig cage is in our living room behind the camera. And They're very disturbed by this scientific experiment in the kitchen. Okay, so we've got our dry ice with some insulation, and then on top of the dry ice is a metal plate. If you're doing this at home, you can use a cookie sheet or a pan, like one of those. Okay, so I'm finished touching the dry ice for now, so I can take my gloves off. And the next thing we're going to do is saturate a pad for the alcohol on what will be the top of our tank. So I have an old towel that I cut up and glued onto the bottom. You can use felt. I think anything that's absorbent is fine. And we want the pad to be soaked, but not really dripping. I'm sure there's problems with the way I'm handling this chemical, but so I have doused the pad, and then I'm tilting it to see if it's saturated. That looks good. I've got a couple of dry spots though, so I don't want any dry spots. This time, there are probably people who are really upset that I'm using rubbing alcohol for a science experiment instead of using it to disinfect, but okay, so I've got a soaked pad of alcohol on top, or what will be the top, and the next thing I need to do is provide a way for an airtight seal. So before I started recording, I rolled out some snakes of Play-Doh. I stole some of my son's Play-Doh, and I'm going to use the Play-Doh as something like plumber's putty to make an airtight seal between the rim of the tank and the aluminum plate below. I found this part to be the trickiest, getting the seal. When I've had failures of cloud chambers, they are usually because I have a spot where air is coming into the tank. Then I'm going to flip it upside down, trying to keep the Play-Doh in place. Not bad. And then I'm going to mash it down to make that airtight seal. Oh, nope, I missed a bit right here. So like I said, this is probably the trickiest part. Well, aside from finding the rubbing alcohol at this time in our lives, this is the tricky part. So I'm going to mash it down to make that seal. And then I want a temperature difference. So on top of the tank, I'm going to put a heating pad. It's like a sore muscle heating pad. Try to make it so that you can still see what's going on in the tank. And then I found adding a weight on top tends to help keep the seal. So now we're going to need to wait. We need to wait for this alcohol cloud thing to form on the inside of the tank. And while we wait, I think I will add some more putty around the edges just to be super sure that I've got this sealed up. It takes about 10 minutes to get the conditions needed to see the particle tracks. So I'll see you back in about 10 minutes. Okay, it's been about 10 minutes, and I have a very cold bottom and a warm top, and alcohol vapor in a supersaturated state inside. I'm going to have to move now, I think, into the bathroom because I can't control the light enough in my kitchen and family room. But the next step is to try to see the particle tracks. And the way we'll do that is to shine a light. So I've got some LED strip lights, and we'll be shining the light down onto the bottom, to that bottom plate, and we'll be looking for something that looks a lot like contrails. I actually just saw a nice big fat track. Oh, and another one. So it's happening right now. These are happening all the time. Particles are all around us all the time. We're just trying to see evidence of them. So we'll move into a darker room, and we'll try to catch some of these tracks on video. Well, my dears, my life gets weirder and weirder every day. Welcome to my bathroom. As you can see, the setup is the same. I have the same cold bottom and warm top, and the lights now are illuminating, trying to illuminate the bottom plate, so the cold plate. And I've turned the video to higher resolution. I recognize that there is a lot of weird glare. If you look closely though, you can see what looks kind of like snow falling, kind of mist or snow. It's easiest to see just a little bit above the black plate. I think I'll try moving this light over to here. It's real hard to get the lighting conditions just right and get the camera in a position where I can see through this plastic tank. Okay, so I can, as I was saying, let's try to put this a little bit sideways here. As I was saying, we are looking across the black surface of the metal plate. It looks a bit like a mist falling onto the black plate. And then through the mist, every few moments, there's something that looks like a faint contrail. So the white path left behind by airplanes. I'm seeing a lot of long straight lines in the right side of the screen. Ooh, I saw a super long line just now across the bottom. I see some shorter, thicker lines. And again, we're looking through this kind of falling snow or falling mist. We're looking for the paths that become apparent through the mist. As the mist falls. So you basically just have to be patient and watch. There was a couple. So some of the tracks are very long and straight. Some are short and thick. Some are fainter than others. These tracks are three-dimensional. They're happening through the whole of this mist. So I don't think we see the tracks very well that aren't parallel to the plate. If I had a big enough magnet, we could make them all parallel to the plate. But that is beyond my kitchen technology. I'm going to shift this over a little bit and see if we can get, there's a better perspective. So again, we're looking through this mist and we're looking for these little lines. Some of them almost look like dots or blobs. Some of them are longer and straighter. They happen pretty fast. And as soon as you see the path, the ionized particles, or I guess it's not, there was a Z in the bottom. So some are straight, some are zigzaggy, some are swirly. As soon as the path becomes apparent, however, this mist is falling, so essentially the cloud is pulled down to the surface of the plate by gravity. So even if a path is very straight at first, as the cloud falls, it becomes a little bit less straight. It's mesmerizing. All right, well, there you have it. You've been doing physics in the kitchen and physics in the bathroom. It turns out an interior windowless bathroom is the perfect place to use a cloud chamber. I hope you were able to see some of those tracks. I will also link a video that shows a professional cloud chamber with great photography and some slow motion. And it will be even easier to see the tracks. What I could see with my eyes in real life was much clearer than what I was able to catch with the video. So if you have any rubbing alcohol and an empty fish tank, I highly recommend trying this on your own. It is amazing to see in real life.